topic about the structure of Mendele's periodic table, modern periodic table. Also, we have learned the electronic configuration in case of periods, groups, and the blocks. And in the last lecture, we have seen the relation between effective nuclear charge and the screening effect. So today, we are going to learn about the periodic trends in the physical properties. So I am going to share my screen with you all and let us begin with the topic. So students, we are going to learn the periodic trends in the physical properties. So there are total 5 physical properties are there. Atomic radius, ionic radius, ionization enthalpy, electron gain enthalpy, and electronegativity. Out of these, first of all, we are going to learn the periodic trends in the atomic radius. But before we learn the periodic train in the atomic radius, first of all, you should know the relation between the screening effect and the effective nuclear charge. So let us revise a few things from our previous lecture. Now, students try to recollect that atom shows presence of nucleus at its center. Nucleus is positively charged and it is surrounded by negatively charged electrons which are revolving around the nucleus in the stationary orbits. Now, as the electrons are negatively charged, what will happen? They show repulsion in between them and hence the shell goes away from each other. Because of this reason, these outer electrons, they are not able to experience the actual nuclear charge. So, whatever the charge is experienced by them, they are referred as effective nuclear charge. Now, electrons which are present in the orbits, these inner electrons or the core electrons, they try to build a wall or they try to screen the outer electron from the nucleus. So if the inner electrons are more, obviously the screening effect is more. So therefore, if the screening effect is more, then in that case your effective nuclear charge is less. So this relation you should keep it in your mind. Effective nuclear charge and the screening effect both are inversely proportional to each other. So by making the use of this, we are going to learn the periodic trends in all the 5 properties. So out of this, first we are going to begin with the periodic trends in the atomic radius. Now, students, please remember that atoms do not have a definite boundary and therefore it is not possible to calculate the exact radius of an atom. So therefore, radius of an atom can be calculated by considering an internuclear distance between the two atoms and therefore atomic radius is nothing but it is a half of the distance between the nuclei of two atoms. Now, atomic radius can be calculated in case of non-metals as well as metals. So out of this, first we are going to learn the atomic radius in case of non-metals. So when we are going to learn the atomic radius in case of non-metals means except the noble gases. Now, please do remember that in the case of non-metals, the atoms of the elements, they are bonded to each other by the covalent bonds. And therefore, bond length of this single bond is equal to sum of the radii of two single bonded atoms. Hence, covalent radius or atomic radius is equal to bond length of a single bond divided by 2. Now, let us elaborate this point with the help of examples in the next slide. See here. In case of chlorine molecule, these two chlorine atoms, they are bonded through this single bond. So, the bond length of chlorine-chlorine single bond is 198 picometer. Obviously, atomic radius of chlorine atom is equal to how much? 198 divided by 2. That is 99 picometer. Now, similarly, you can able to calculate the bond length in case of diamond. So in case of diamond, you can calculate the bond length of carbon-carbon single bond and which is nothing but 154 picometer and hence the atomic radius of carbon can be calculated as 154 divided by 2 that is nothing but 77 picometer. So here we have learned how to calculate the atomic radius in case of non-metal. Now we are going to learn how to calculate the atomic radius but in case of metals. See here, in case of metal, the atomic radius is also referred as metallic radius, and it is nothing but it is a half of the distance between the centers of two adjacent atoms in case of metal. Here we have taken the example of barium. So we are going to calculate the atomic radius of barium. See here, in case of barium, the internuclear distance between these two beryllium atoms is how much? 224 picometer. So obviously the atomic radius of barium, how you will calculate it? 224 picometer divided by 2. That is nothing but 112 picometer. Correct? So here now you come to know that how to calculate the atomic radius in case of non-metals as well as how to calculate the atomic radius in case of metals. Now our job is we are going to learn the periodic trends with respect to atomic radius in case of across the period and down the group. Yes, but before that you should know what is the exact definition of atomic radius. So how will you define the atomic radius in case of metals and non-metals? See, in case of metals, we can define the atomic radius as it is nothing but it is a half of the internuclear distance between the two adjacent atoms. Whereas in case of non-metal, how will you define the atomic radius? It is nothing but it is a half of the internuclear distance but between two single bonded atoms. So you have to remember this definition: atomic radius in case of metals and atomic radius in case of non-metals. So now you come to know about the atomic radius in case of metals and non-metals. So let us study the periodic trends in the atomic radius across the period and down the group. So out of this, first we are going to learn the periodic trend in atomic radius across the period. Okay, now here, to explain this part, we have considered an example of elements from the period number 3. Now, all of you know that in case of period, as you move from left to right, what will happen? Atomic number goes on increasing and it increases by 1. See here, sodium atomic number 11, magnesium it is 12, aluminium 13, silicon 14 and so on. So as we move from left to right, atomic number goes on increasing and increases by 1. But here, whatever that additional electron is there, that is added into the same shell because we are dealing with a single period. So therefore, here it is written atomic number increases by 1, but the shell remains the same. Meaning is what? That electron is added to the same shell. Now, electrons are added to the same shell, but nuclear charge increases by 1. Charge is more, effective nuclear charge is more. Effective nuclear means Z to the base EAA. That effective nuclear charge is more and hence outer electrons are tightly held by the nucleus. And because of that reason, there is a reduction in the size of an atom. Just look at this diagram. See here, the sodium atomic size, if you compare this with the chlorine, you will come to know that atomic size of the sodium is larger, whereas atomic size of the chlorine is smaller. Because as you move from left to right, your nuclear charge goes on increasing, hence your screening effect remains the same, but effective nuclear charge is more, and as effective nuclear charge is more, outer electrons are tightly held by the nucleus, hence there is a reduction in the size of an atom, and therefore we can say that atomic radius decreases along the period. Now just read out these things. These are the things whatever we have discussed right now. See what is written: atomic number increases, number of proton increases, newly added electrons, they get accommodated in the same valence shell. Hence, the Screening effect remains the same, but effective nuclear charge goes on increasing So what if it results in decrease in the atomic size? So here we have completed the periodic train in atomic radius across the period. Now we are going to learn the periodic train in atomic radius but down the group. Okay. Now see here. In the case of group, again we can say that as you move down the group, what will happen? Your atomic number goes on increasing, obvious. But at the same time, just look at here, number of shells goes on increasing. As number of shells increases, but here the number of electrons increase. Hence, what will happen as you move down the group? Shell number goes on increasing, electrons goes on increasing, and hence outer electrons, they are loosely held by the nucleus because here more number of electrons, hence screening effect will be more, but nuclear charge will remain the same. As your screening effect is more, outer electrons are loosely held by the nucleus. As the outer electrons are loosely held by the nucleus, and because of this reason, what will happen? Size goes on increasing. Just you compare it. Beryllium atomic size is smaller, but here for the barium, just look at this. There is an increase in the size of an atom. So just look at the screen, whatever we have discussed right now, it is written over here. See, as we move down the group, atomic number increases. Hence, nuclear charge increases. Simultaneously, number of electrons in the atom also increases. Yeah, that means as you go on, as you move the downward direction, obviously shell number is also increases. And hence, what will happen? Your screening or the shielding effect is more. Because of this reason, these valence electrons or the outer electrons are weakly held by the nucleus, and hence your effective nuclear charge decreases. And what it results in what? Because of this reason, atomic radius increases as you move down the group. So here we have covered our first physical property, and that is nothing but the atomic radius. Now we are going to learn the periodic trains in our second physical property, and that is nothing but the ionic radius. So this is about the summary of the periodic trends in atomic radius. So here we can conclude that as you move from left to right, atomic radius decreases, and as you move down the group, atomic radius increases. So let us switch over to the next slide for learning the periodic trends in case of ionic radius. Now see here. In case of ionic radius, we can say that ionic radius is nothing but it is a distance between nucleus and valence shell electron of an ion. But again, very similar to that of the atom, we can say that ions do not have a definite boundary. Therefore, ionic radius can be calculated as it is a half of the distance between neighboring cation and anion. Hence, ionic radius can be calculated as, see, radius of anion and plus radius of cation divided by 2. So this is a formula to calculate the ionic radius. Radius of anion plus radius of cation divided by 2. Now, just look at this diagram. From the diagram only you will come to know that there is a difference in the size of cation as well as anion. Cations are smaller in size, whereas anions are larger in size. What is the reason behind it? Why this so? So we are going to reason out for these two questions, but in the next slide. Now see here. This is our question. Why is the cation smaller than atom from which it is formed? Or another way of asking question is why the cations are smaller in size than that of their parent atom? Now see here. First of all, you should know that how the cations are formed. Cations are generally formed when an atom loses one or more valence electron or the outer electron. Then it results in the formation of positively charged species and which is referred as cation. Now, To explain this part, we have taken the very simple example of sodium atom. See, in the case of sodium atom, it has got one valence electron. So when the sodium atom loses this one valence electron, it results in the formation of this positively charged species, that is cation. See here, this sodium indicates it is only sodium atom, but this positively charged indicates this is a sodium cation and which is formed from this parent atom. So in this cation, if you look at this diagram, you will come to know that as cations are formed after loss of electron, so in the cation, number of electrons are less, but nuclear charge remains the same as that of the parent atom. Nuclear charge remains the same means number of protons are same in the cation as that of the parent atom. But here, sorry, number of electrons are less. Now, try to recollect that relation, effective nuclear charge and the screening effect. As number of electrons are less, but nuclear charge is same, obviously what will happen here, effective nuclear charge is more. So these outer electrons are tightly held by the nucleus, and hence there is a reduction in the size of an cation. So that is why we can say that the cations are always smaller in size than that of the parent atom or than that of the atom from which it is formed. Very similarly, we are going to reason out for our second question that we'll study in the next slide. Okay, now our second question is, why is the anion larger than the atom from which it is formed? Means, or in another words, you may come across with the question, why the anions are larger in size than that of their parent atom? Again, first of all, you should know that how these anions are formed. See, when the atom gains one or more electron, it results in the formation of anion. Here, we have taken a very simple example of chlorine atom. In the case of chlorine atom, when it gains one electron, it results in the formation of chloride ion. Now see here, if you look at this diagram, you yourself will come to know that in the case of chloride ion, the number of electrons are more as compared to this chlorine atom or the parent atom. But what about the nuclear charge? The nuclear charge will remain the same. Means the nuclear charge for the anion is same as that of the parent atom. When I say nuclear charge is same, in the sense number of protons are same in the cation as that of their parent, as that of their present in the case of parent atom. So for the anion, your proton number is same as that of the parent atom. Now see here, in the case of anion, now the number of electrons are more. Nuclear charge is same. As the electrons are negatively charged, they show the repulsion in between them, and hence the shells go away from each other. As the shells go away from each other, obviously what will happen to the size? The size goes on increasing, and hence in the case of anion, always the anions are larger in size than that of their parent atom or than that of the atom from which they are formed. So basically, in the when you will learn the periodic trains in the case of ionic radius, these two give reason type of questions are very very important, because generally they will ask you the question in the give reason type of question, generally asked for the 2 marks, why the cations are smaller in size than that of the parent atom. Also they may ask you the question, why the anions are larger in size than that of the parent atom. So now we are going to learn the periodic trains in the case of ionic radius. Now, periodic trends in the ionic radius is very similar to that of the atomic radius. That is, ionic radius is also decreases across the period as you move from left to right. Whereas, as you move down the group, what will happen? Ionic radius goes on increasing as you are moving from top to downward direction. So here we have covered our second physical property, that is nothing but the ionic radius. Now after that we are going to learn a new concept, and that is about the isoelectronic species. So let us learn that part. Isoelectronic species is nothing but what? Iso means same. So isoelectronic species are those atoms and ions which contain same number of electrons. As they show the same number of electrons, but they differ in their radii. Now, why they differ in their radii? Because their actual nuclear charge is different. This is the important thing. This is a key point. Isoelectronic species means atoms or the ions contain same number of electrons, but they differ in their radii. Why they differ in the radii? Because their actual nuclear charge is different. What do you mean by this statement? Nuclear charge, actual nuclear charge is different in the sense, more is the nuclear charge, obviously, more will be the attraction for valence electron by the nucleus, and hence what will happen? There is a reduction in the size of either atom or an ion. Correct? So we are going to elaborate this point with the help of examples in the next slide. Now see here. Here we have taken the example of fluorine atom. Atomic number of fluorine atom is 9. Means for the fluorine atom there are 9 protons and 9 electrons. Now you know that how the anions are formed. When an atom gains one or more electron, it results in the formation of anion. So when fluorine atom results in the formation of fluoride ion, how it forms? When the fluorine atom gains one electron, it results in the formation of fluoride ion. For the fluorine, it has got 9 proton, 9 electron. So after gaining of 1 electron, now the fluoride ion will show total 10 electrons, but your proton number will remain the same, that is about the 9. Now, in the case of sodium, atomic number for sodium is 11. How the cations are formed? When the atom loses one or more electrons, it results in the formation of cation. So, for the sodium, it has got 11 proton and 11 electron. After loss of electron, now the sodium cation will show 10 electrons, but its proton number will remain the same. That is nothing but the 11. Just look here. As the fluoride ion has total 9 proton, nuclear charge for the fluoride ion is plus 9. As the sodium cation has got total 11 proton, the nuclear charge for the cation is plus 11. Now, if you compare the nuclear charges of both, you will come to know that for the cation, your nuclear charge is more. And you know that if the nuclear charge is more, there's a greater is the attraction for valence electron by the nucleus. Obviously, there's a reduction in the size of an cation. And therefore, and therefore, in the case of fluoride ion, your ionic radius is 133 picometer, whereas in the case of sodium cation, your ionic radius is 98 picometer. Okay, it has got 98 picometer. So therefore, from this you can clear cut, you will come to know that ionic radius of cation is smaller than that of the fluoride ion. Correct? So this is the way we have covered what you mean by isoelectronic species. And now we are going to learn our third property, and that is nothing but the ionization enthalpy. Now, for this, definition is highly important. What is the definition of ionization enthalpy? The definition is, it is the energy required to remove the electron from the isolated neutral gaseous atom in its ground state. Now see here, the ionization enthalpy is a very important because it's a favorite question of the examiner. Generally, whenever the definitions are asked, this definition is there in your paper that define the ionization enthalpy, 1 mark per question if it is asked. So now we are going to learn what do you mean by ionization enthalpy in the detail. Now see here. First of all, you know that when there is a removal of electron from the neutral atom, it results in the formation of cation. See here, removal of an electron from the neutral gaseous atom. Here X is the neutral atom which is in the gaseous state. When the electron is removed, it results in the formation of positively charged species, and that is nothing but the cation. So here we have taken the example of sodium atom. Simple example. We have seen in earlier part also. When the sodium atom loses this one valence electron, it results in the formation of this positively charged species, and that is nothing but the cation. So now let us learn two more things about the ionization enthalpy. Here, ionization enthalpy is a short form. So ionization enthalpy is nothing but it's a quantitative measure of tendency of an element to lose the electron. It is symbolized by delta IH, and it is unit for the ionization enthalpy is kilojoule per mole. Now, the key point for the ionization enthalpy is ionization enthalpy is always it is positive, because obviously energy is required to remove the electron from the neutral atom, and hence ionization enthalpy, that is delta IH, is always positive. Now, one more important thing, that is nothing but, since at a time only one electron is lost from the given element, and therefore we have first ionization enthalpy, second ionization enthalpy, third ionization enthalpy are possible. See, I repeat, at a time only one electron is lost from the given element, and therefore first, second, third, fourth ionization enthalpies are possible for that particular element. Now, let us study how to express those ionization enthalpy. See, the first ionization enthalpy is expressed as, this is your neutral atom, that is X, which is in the gaseous state. When it show the loss of one electron, you know that then there, whenever there is a loss of electron, it results in the formation of positively charged species, and that is nothing but a cation. So it results in the formation of positively charged species, that is cation. So we can express or we can represent this ionization enthalpy as delta IH1. Now, how you will express the second ionization enthalpy? Your second ionization enthalpy can be expressed as, now here for the second ionization enthalpy, now there is a loss of electron from this cation, that is positively charged species. So that's why we have mentioned here X plus, that is which is in the gaseous state. When it show the loss of electron, it results in the formation of X2 plus, obviously. And this ionization enthalpy can be expressed as delta IH2. Now, if you look here, you will come to know that value of second ionization enthalpy is greater than the first one, and the value of third ionization enthalpy is greater than the second one and the first one, and so on. Why? What is the reason behind this? Simple. What happens in the case of second, how you will get the second ionization enthalpy? When there is a loss of electron from this positively charged species. Now, positively charged species is nothing but what? It is a cation. And you know that in the case of cation, the size is small, because here the nuclear charge remains the same. But how the cations are formed? After loss of electron, the cations are formed. So therefore, in the case of cation, as there is a loss of electron, so and the nuclear charge is more, so outer electrons are tightly held by the nucleus. And because of that reason, more energy is required to remove the electron from that cation, and hence always second ionization enthalpy is greater than the first one, and hence the value of third ionization enthalpy is greater than the second one, and second ionization enthalpy value is greater than the first one. So this is about the what do you mean by ionization enthalpy. Now let us study the periodic trains in case of ionization enthalpy. Okay, now to learn the periodic trains in the ionization enthalpy, here we can say that as you move down the group, ionization enthalpy goes on decreasing. So here, to explain this part, we are going to take the help of our explanation of the first physical property, and that is nothing but the atomic radius. Now see here, try to recollect the part which I have explained in the beginning of this lecture. As you move down the group, you know that atomic radius goes on increasing, correct? Now why the atomic radius goes on increasing? Because you know that as you move down the group, atomic number increases, but see here, number of shells also increases. As the number of shells increases, what will happen to the electrons? Electrons increase. As number of electrons are more, screening effect is more, effective nuclear charge is less, and because of the screening effect, outer electrons are loosely held by the nucleus, and therefore as you move down the group, your atomic radius goes on increasing. Now, try to relate the things. When the atomic radius goes on increasing, means valence electrons are loosely held by the nucleus. So obviously, less energy is required to remove those electrons. And therefore, as you move down the group, as the outer electrons are weakly held by the nucleus, very less energy is required to remove the electron. So therefore, ionization enthalpy goes on decreasing as you move in the downward direction. What about the period? As you move across the period, you know that atomic number goes on increasing. Atomic number increases, nuclear charge increases, but the newly added electron gets added to the same shell. As the electrons are added to the same shell, inner electrons are same, screening effect remains the same, but now here effective nuclear charge is more. So obviously what will happen? Outer electrons are tightly held by the nucleus, and hence there is a reduction in the size of an atom as you move across the period. So obviously size is less and more energy is required to remove those electrons, and therefore ionization enthalpy ionization enthalpy goes on increasing as you move across the period, correct? And therefore, in the case of alkali metals here, it has got lowest first ionization enthalpy, but in the case of inert gases, it shows highest first ionization enthalpy. So here we come to know that okay, that as you move down the group, ionization enthalpy decreases, and as you move across the period, ionization enthalpy increases. However, few irregularities are seen across the period. What are those? That we study in the next slide. Now see here. These two major irregularities are seen. That is, ionization enthalpy of boron is smaller than the beryllium, though atomic number of beryllium is 4 and boron is 5. The second given type of question is ionization enthalpy of oxygen is smaller than the nitrogen, though the atomic number of nitrogen is 7 and the oxygen is 8. Let us reason out for both the questions in the next slide. See here. We are going to solve the first question. Ionization enthalpy of boron is smaller than beryllium, though the atomic number of boron is 5 and beryllium is 4. Now see here. How you will write the electronic configuration of boron. Atomic number of boron is 5. So EC is 1s2, 2s2, 2p1. In the case of beryllium, electronic configuration is atomic number is 4, 1s2, 2s2. Now, if you look at this valence shell configuration for the boron as well as beryllium, you will come to know that in the case of boron, it has got only one electron, the 2p orbital. So, therefore, it is easy for the boron to lose the electron from 2p orbital because 2p orbital has a less penetration than 2s orbital. Hence, it is easy to remove the 2p electron from the 2s electron. Correct. Now, you may wonder, there is a question in your mind, what do you mean by this part? This 2p orbital has got the less penetration than 2s orbital. See, this is because if you compare the 2s and 2p orbital towards the nucleus, you will come to know that 2s orbital is closer to the nucleus, but 2p orbital is little far from the nucleus. So obviously, as the 2p orbital is little far from the nucleus, less energy is required to remove that valence electron from the 2p orbital rather than 2s orbital, and therefore ionization enthalpy of boron is always less than the ionization enthalpy of beryllium, though the atomic number of boron is 5 and beryllium is 4. Correct? Now, in the next slide, we are going to reason out for our second question. Here, ionization enthalpy of oxygen is smaller than the nitrogen, though atomic number of nitrogen is 7 and the oxygen is 8. Again, here we are going to take the help of our electronic configuration for the nitrogen and the oxygen. In case of nitrogen, the atomic number is 7. So the electronic configuration is 1s2, 2s2, 2p3. 2p3 is written as 2px1, 2py1, 2pz1. See, x, y, and z, these are the orientations of the orbital, but we have not mentioned here. You will come to know into the detail of that part when you will go through the chapter structure of an atom. At present, you just remember that these 2p orbitals are expressed as 2px, 2py, and 2pz. So coming back to a point, we are saying that this as atomic number is 7, so here EC will be 1s2, 2s2, 2p3. So these 3 electrons, they accommodated in the 2p orbital in such a way that they show they are they you know they are half filled 2p orbitals, and they give extra stability. They gives the extra stability to the nitrogen, and hence more energy is required to remove the electron, because you know that half-filled orbitals always give the extra stability. So more energy is required to remove those electrons. But what about the oxygen? In case of oxygen, your atomic number is 8. So your EC is 1s2, 2s2, and 2p4. Now, how these 4 electrons are accommodated in these orbitals? They are accommodated as per the Hertz's rule of maximum multiplicity. Then what was that rule? See, the meaning of the rule is when the orbitals in the ground state are available, then they are filled with the electron singly with the parallel spin, and then in the pairs with the anti-parallel spin. See, the parallel in the sense when the arrow is in the upward direction, it is referred as electrons are in the parallel spin. When the arrows are in the downward direction, they are referred as anti-parallel spin. Again, this rule and these notations you will learn in the detail in the chapter structure of an atom. At present, you just remember that here, as per the Hertz's rule, how these 4 electrons are accommodated? First 3 electrons are occupy this orbital singly with the parallel spin, and remaining the fourth one will enter into this 2px orbital. As in the case of this 2px orbital, there are 2 electrons are present. There is electron-electron repulsion in the doubly occupied 2p orbitals, and therefore, obviously, less ionization enthalpy is required to remove the electron from the 2p orbital, and therefore, ionization enthalpy of the oxygen is less than ionization enthalpy of nitrogen. So here we have covered all the 3 properties, and here we have actually conclude our today's lecture. So what we have learned in the today's lecture, we have seen the periodic trends in the atomic radius, that is how the atomic radius decreases as you move across the period from left to right, and how the atomic radius increases as you move down the group. Also, we have seen the periodic trends in the ionic radius, that is how the ionic radius decreases as you move across the period from left to right, and the ionic radius increases as you move down the group. Further, in the ionic radius, we have seen the 2 division type of questions: why the cations are smaller in size than the parent atom, and why the anions are larger in size than the parent atom. Also, we have seen the concept of isoelectronic species. Then, after that, we have learned the periodic trends in ionization enthalpy, how the I is increases across the period, and how the ionization enthalpy decreases as you move down the group. And also, we have seen few irregularities in the case of ionization enthalpy. So, I think that's it for the today's lecture, and thank you all of you. Thanks.
Okay, thank you, ma'am.